In the last lecture, I stopped at this one, right? This how many different strings can be made by reordering the letters, right? Any doubts now? Yeah. Syllabus 4 will be up to chapter 4. Chapter 4. Yeah. Medicine starts from, I think, Feb 15. And there is no, not much gap between end sem and mid sem. So I'll be just covering this today and then we'll go for revision, okay? So, how many ways are there to place 10 indistinguishable balls in 8 distinguishable bins? So, how many ways are there? See, 10 indistinguishable balls you are putting in 8 bins. Okay, that means you want 10 things distributed over 8, right? That is x1, x2, and so on. If x1 number of balls are going into first bin, x2 and so on up to x8 are going into 8th bin. Total number of this sum will be 10. Okay, and you know that number of solution for this one, that is integer solution, will be when repetition is allowed, right? So this means we have done k is running from, or you can just say I is running from 1 to n, and this will be equal to r, right? I is running from 1 to n. So solution for this one, number of solutions for this one was n plus r minus 1 combination CR, right? So here it will be 8, n is 8 plus 10 minus 1 C 10. Okay, so that will be your number of solution, and that will be the number of ways. That is how many ways are there to distribute 10 over 8 different this one, and these are indistinguishable. Okay, that is we cannot differentiate this 10. Okay, so that sum will be 8. Okay, and this is coming as 17 C10. Okay, and 17 C10 is coming as this one. Clear? Yeah.
Yes, ma'am.
Similarly, you have how many ways are there to select? Here you want to select 5 unordered. So order doesn't matter, means combination unit. 5 unordered element from a set with 3 elements. So you have only 3 elements. Out of that you want to select 5. Means to say repetition is allowed. Obviously repetition is allowed, only then we can select 5 out of 3, right? So even if it is repetition is not written, even if this sentence is not written, obviously it is understood you want to select 5 out of 3, means repetition should be allowed. In that sense, when repetition is allowed, it can be given by n plus r minus 1 CR. Okay, so that is here r, that is r combination you need, and how many combination? 5 combination, right? You need 5 combination out of 3. So n is equal to 3 and r is equal to 5. Okay, and repetition is allowed, means 3 plus 5 minus 1, 3 r. R is again 5. So this will be 7C5. And 7C5 is 21. Clear? Now if I replace with r with 3 and n with 5, that is how many ways are there to select 3 unordered elements from a set with 5 elements. So if it is not written, so it will be, repetition is not allowed. Okay, that is 5C3. Okay, but it's written that when repetition is also allowed, then it will be n is equal to 5. You want total number of elements are this 5, and you want to select 3, right? So 3 combination will be given. It is 5 plus r minus 1, 5 plus 3 minus 1, CR. That is coming as 7C3 35. Okay? Clear?
Yes, ma'am.
Similarly, you have this one, and this is the last question of this chapter. A bagel shop has onion bagel, poppy seed bagel, egg bagel, salty bagel. So first kind, second kind, third, fourth type, fifth type, pumpernickel. Sesame is sixth type, raisin seventh type, and plain is eighth type. So 8 number of different bagels it has. How many ways are there to choose 6 bagel? 6 bagel you want to choose, means 6 combination you need. Okay, 6 combination. Obviously repetition may be allowed, right? Any 6 you can choose. You can choose all onion bagels, right? So 6 combination when n is different kind. How many? 8, right? When n is 8 and you need 6 combination, repetition is allowed. So how many ways are there? Formula is n plus r minus 1, right? N plus r minus 1, C r. So just put n is equal to 8. 8 plus 6 minus 1, C 6, right? So that will give you solution for 6 bagel. A dozen bagel. You want 12 combination. Okay, you want to choose 12. A dozen bagel. N is equal to 8. Okay, this is n plus r minus 1, C r again. So it will be 8 plus 12 minus 1, C 12. Okay, 2 dozen. 24 combination you need. Okay, 24 combination. N is equal to again 8. Total number of different bagels are, total type of different bagels are, we have 8. So it will be 24 plus that is 8 plus 24 minus 1, C 24. Okay, so like that you can calculate up to C part. What about D part? A dozen bagel, at least one of each kind. At least one of each kind means you will select one from here, one from here, one from here, one from here, one from here. That is 8 bagels out of 12. 12 you can write 8 plus 4, right? That is 8. You need to select different kind. That is only one way, right? And 1 into this 4. These 4 you can select out of these 8. Okay, so the remaining thing is you need to select 4 out of, there is 4 combination. Repetition may be allowed. So you can select all the onion bagels, all this one, or 2 or 3, 2 or 2, like that, 2 1 1, like that, right? So the remaining is 4. You need to select 4 combination out of 8. N is 8 and R is 4. So how many ways are there? That is 8 plus 4 minus 1, C4. Okay. This much number of bagels for this one, and one number of this one. So 1 into this one. It will be 11C4. So finally you got 11C4. Okay. So how many? Tell me all answers. So this one it is 8 plus 6 minus 1, that is 13, 13C6, right? Here you have 8 plus 12 minus 1, 19, 19C
12.
12. And here you have 8 plus 24 minus 1, 33, 31, right? 31C 24. And finally you got 11C4. Okay? Any doubt? Anyone having any doubt in chapter 5?
Can you show the above question once? Okay, ma'am.
The first one will be 13C6, that is coming as 1716. For second one, 19C12, that is coming there. 31C14, you have this one. And the final one is 11C4, that is 330. Okay? Clear? And then we are left with only chapter 6. So that we will be starting after mid-sem, or we'll see. Okay? I asked you to revise chapter 1 and 2.
Yes, ma'am.
Yes, ma'am.
Chapter 1. We'll be just covering chapter 1 today. Chapter 2 is for next day, whenever you have tomorrow, right?
Yes, ma'am. Tomorrow.
So tomorrow, chapter 2. Yes, any doubt in chapter 1? रिवाइज किया भी है या नहीं?
Ma'am, predicates and quantifiers.
Okay, predicates and quantifier. Anything else? So any doubt in this?
Proofs.
No doubt. Proposition, compound proposition, logical operators, negation, conjunction, disjunction, conditional, biconditional. Then for conditional, we have converse, contrapositive, inverse. Any doubt in this? Converse will be for P implies Q implies P. Contrapositive will be negation Q implies negation P. Inverse will be P implies Q. For this one, it will be negation P implies negation Q. No need to change the format. Just whenever whatever the statement given P implies Q, just put not P and not Q. Okay.
Yes, ma'am.
You will get the inverse part. And if you want to change the format, then go ahead, no problem. But remember these things. Okay. That is P implies Q can be expressed in English is this one. Okay. If is always coming with P. Okay. Except one condition, that is only if. Only if comes with Q. Okay. Whenever is also coming with P. When is also coming with P. Okay. It could be also whenever P comma Q. When P comma Q. Okay. P implies Q. Q follows from P. P is sufficient for Q. Q is necessary for P. Okay. Then we did biconditional. If and only part. Solve some question. Translation part. From logic to English, English to logic. Converse, contrapositive, inverse questions. Then we did propositional equivalence. On the basis of this compound proposition can be classified into tautology on the basis of truth values, tautology, contradiction, and contingency. If it is always true, it is tautology. If it is always false, it is contradiction. If sometimes false, sometimes true, it is contingency. Okay, that is neither tautology nor contradiction. It will be contingency. Okay. Compound statement is two or more compound statement are logically equivalent if they are having same truth values. Okay. Then we did some questions based on tautology. based on logical equivalence. When you have two main statements, P and Q, how many rows will be there in truth table? 4. If only one main statement, 2, that is 2 raised to power 1. If 2 P and Q are there, so 2 raised to power 2. PQ are 3 main statements, that is 3 elements, let's just say 2 raised to power 3, 8. Okay? And whenever n, 2 to the power n. Okay?
Yes, ma'am.
Any doubt in tautology and logical equivalence? We'll start with this.
No, ma'am, no doubt.
No doubt. Good. Predicates and quantifiers. We have done some statements containing variable. For example, x is greater than 1. Is this proposition? No, it's not a proposition. It does not have any particular truth value, right?
Yes.
It is not true, not false, until we give some value to x, right? So if we assign some value to x, only then it becomes proposition. So these type of statements which contains variable, these are known as predicates. Okay, here x, the variable, is the subject of the statement, and the remaining part is
Predicate.
predicate. That is x is greater than 1. Okay, so is greater than 1, this part is predicate and this is variable. We represent by capital letters and then this function type. Okay, bracket x. Okay, so this is ax, px, qx, rx, sx like, right? So it will be known as predicate function.
Yes, ma'am.
You will talk about the truth value if you assign some value. For example, x greater than 3 is px, predicate function px. What are the truth value of p4? If you put 4 in place of x, it will be 4 greater than 3. So is it true? Yes, it is true, right? If you put 2, then it will be false, 2 greater than 2, right? So its truth value will be false. Like this, you can have 2 variable predicate function, right? X is equal to y plus 3. So you can talk about truth value if you give both variable as some value. Okay. Got it?
Yes, ma'am.
One way is just assigning some particular value to the x. Quantifying by using quantification. Quantification is the process to make the predicate function as proposition. Okay. One is by using universal quantification. Another is by using existential quantification.
Quantification.
So for universal quantification, you use the quantifier for all. Okay. After quantification, for this one you need domain. For quantification, you always need domain. Okay. If it is given, then it's okay. Otherwise, you'll ask for this. Okay. Quantified statement is for all x px. Okay. For all x px, for each x px, for every x px. Okay. This is the translation for this. Okay. Now, when this will be false and when this will be true for all x px, and x is coming from domain. As the name suggests, that for all x px, if px is true for every x, in that case for all x px will be true. Okay, px is true for each x, for all x in the domain. Only that it will be true. Otherwise, if px is false for single x, even for a single x, then it will be false. That is, there is some x which for which px is false. Okay, which makes px as false. In that sense, for all x, this quantification will be false. Okay. Another quantification is that is existential quantification. That is denoted by there exists x px. Here there exists this is existential quantifier. There exists. Okay. Now when this will be true, there exists x px. So that px means px is true even for a single x. In that it will be true, right? If px is true for even for at least one x, then it will be true. This quantification. And when this will be false, it is true for no value. That is, for all the value of x, it is false. Then it will be true, false. Okay. Now we can talk about the truth value of these quantifications, right? Now it has become proposition, right? Px is not a proposition. If you quantify it, this will be a proposition, right? You can talk about for all x px truth value for this one, for a defined domain. Okay, for example, for this one, you have real number and domain is real number. Okay, so you can talk about the truth value of this one. So our all the real number, is the statement true?
Yes, ma'am.
True, right? So this will be
Yes.
True.
now. If I ask you what is the truth value for the statement, if you have there exists x px and px is this one, so will it be true or false?
Always true.
True, right?
True.
True.
And if I give you px as x plus 1 is less than x, in that sense, what about this statement? True or false?
False.
Because there is no value which satisfies this one, right? No real value, no real number that satisfies this one. That is, px is false for all the values of real numbers, for all real number x. That's why this will be false. Okay. For this statement, we need just at least one x, but this is true for every x, so no worry about that. But here we have for all the value of x, px is false. That's why it is false. Yeah, any doubt?
No, ma'am.
Okay, then you have the statement. What is the truth value for the quantification? You have this one, for all x px, and domain is real number. You choose value of x from the real number and check whether it is true for all the real number or not. Obviously not, right? If you put 3, 2.1,
Yes, ma'am.
right? So any value, any real value which is greater than or equal to, even if you put 2, for that also you have false. So this is false then. Existential quantification done. Yeah, English meaning of this one, there exists x px, or there is some x px, or there are few x px, at least one x px. Okay, some x px, like that you will be using logically equivalent statements. So when truth values are same, then you say the statements are logically equivalent, right? So here we had for all x px. Okay, for all x px, this is logically equivalent to conjunction of px is. Okay, this is logically equivalent to if your domain is containing x1, x2, and xn, so it will be conjunction of px1 with px2, px3, and so on up to conjunction pxn. Okay, this is logically equivalent because right hand side is true when all are true, right? And left hand side also true when px is true and all values. Clear? Yes.
Yes, ma'am.
And this is false even for a single value is giving you false, and same for this one. Next, there exists x px. This will be
disjunction of
equivalent to disjunction P of x1, disjunction with P of x2, disjunction of it will be P of xn. Okay, and if you take the negation, then it will be negation of all, then De Morgan's law applied, the conjunction will become disjunction, then disjunction will become there exists, right? That means negation of for all will be equivalent to you got negation of for all will be equivalent to there exists negation. Okay, there exists x negation of px. Okay, and if you apply negation or here, it will be negation or here, disjunction will become conjunction, that will become for all. So that is there exists, negation of there exist will become for all negation. Okay, and the translation part also, I gave you some keywords, that is negation of there exist. Whenever you find negation of for all, you can use not everyone, right? Not all, not everyone, not everybody, right? The keyword is not everyone, not everybody, not every student. Okay, this is for this one. And negation of there exists, it can be used for no one, nobody, no student, right? The keyword is no one. Okay, and I give you one more thing, that is whenever you have px and qx and your, for example, all your friends are perfect, like that, you need to translate into some logical expression from English to logic. So you can use for all x. If that is implication is inbuilt, then you can use for all x, px implies qx. Okay, that is whenever you are using for all, it will be accompanied with implication, unless it is not explicitly given. Okay, that is whenever it is given that all your friends, these are all your friends and they are perfect, there you will be using if explicitly it is and written or but written, there you will be using this conjunction. Otherwise, all are perfect, or everyone is perfect, or all your friends are perfect. In that sense, if you are using two or more these two predicate function that are connected with this implication operator. Okay, that is when you are talking about this universally, and whenever you are talking about a part of that thing, there exists x, then you will be using conjunction to join px and qx. For example, some of your friends are not perfect. Okay, see, means you are having a universal set. Okay, universal set. Then whenever you are taking any x, that means that thing will be implies. I mean that will be true for that. Clear? So for all will be always accompanied with this implies. But if you're talking about some part of this one, then for this one it can be, right? But what about if you put x from here? That is not true for that case, right? For some part, if it is true, then you are saying these are present in this one, That is, these are some of your friends, means X and Y, X, Y, Z. These are your friends and they are not doing that and they are doing that. Okay. That means you are not talking universally. That's why you need to specify that this property does not hold universally. Yes. Implication means those students are in your class, okay, according to your example. Those students, for example, one ABC, okay, 3 students you are talking about. So you are saying some students in this class, but they are not taking discrete mathematics class. Means some students have not taken discrete mathematics course. Okay, means to say some students, about which students you are talking about? Specific students, na? So that's why this is we specifically say that these are the students. There are some students and they are not doing that. But if we take this implication, that means anything, some of these you can choose, or some of the other student you can choose. They are not doing that. Clear? Okay, whenever you are talking about some part of the domain, you always use this conjunction, okay, and to specific about that part, okay. And whenever you are universally saying that, universally you pick any X from anywhere, that will be obviously implication, okay. So then we did the translation part there as well. Translation from logic to English, English to logic. And this one, again translation from logic to English, and here English to logic. The domain, whenever quantifiers are given, domain will be given, okay. Again translation part. Whenever from English to logic, you need to define the domain. So it's up to you which domain you are defining. According to that, translation will change. Okay. Then we did this nested quantifier. Any doubt in nested quantifier?
Yes, ma'am.
Yeah, tell me.
Can you explain once?
Okay, whenever you are using more than one quantifier, that comes under nested quantifier. Okay, that is, you are having this two quantifiers you are using, right? So this for all is applied on this part of this logical expression. And what about this for all? This is applied on this part of logical expression. Okay, so the scope of this outside quantifier is bigger than the scope of this one, right?
Okay,
okay. What does the scope means? The part of logical expression where we are applying this. Okay.
Yes.
Similarly, in this case, for all n there exists. So for scope of there exists is just this much expression. Whatever this for all, it is applied on there exists y, x plus y is equal to 0. Clear?
Yes, ma'am.
Then we did the translation part from English to logic, logic to English. So here one by one you can just take it, but domain will be given for all the variables, whatever it includes. Okay, that is for all x. X is what? Real number. So you need to quantify for all real numbers x, for all real numbers y, or if both are same, you can just say for all real numbers x and y. If this part, then this part, right? So if x is positive and y is negative, then the product will be negative real number. Okay? Or you can just directly write this expression. If x is greater than 0 and y is less than 0, xy is less than 0. Or in more compact form, you can write the product of two real numbers, that is the product of, we are talking about two real numbers, a positive real number and a negative real number is always negative. Okay, the product of a positive real number and a negative real number is always a negative real number. Okay, we can talk about the truth values of this one after quantifications. That is this one, for all x, for all y, for all y, for all x. For all x, there exists y. There exists x for all y, pxy. There exists x, there exists y, there exists y, there exists x, pxy. So this one will be true if pxy is true for every pair of x and y. Okay, for every
Ma'am, you are
pair.
not audible, ma'am.
I'm not audible.
I'm audible.
Check your network connection. This will be true if pxy is true for every pair x comma y, and same for this one. And when this will be false, we know that for all will be false, even for a single value this gives you false, right? So even if we got a single pair x comma y for which pxy is false, in that case it will be false. Okay, so there is some pair x comma y which makes the statement as false. Okay, for that, for all x, for all y, or for all y, for all x, this will be false. Clear? And here it will be true if for every x there exists some y such that pxy is true. That is, for every x you find some y for which pxy is true. And when this will be false, for every x, if you are not able to find any y, that is, for a single x, if you are trying all the y's and you are not you don't find this as true, that means there is some pair, that is, or some there exists some x which makes this false for everyone. In that sense, this will be false. Okay, when this will be true, there is some x that is working for all y, so that pxy is true. Okay, when this will be false, when this will be false, if you take all the x's and you don't find any y such that this as true, that means all the x's you find some y which makes this as false. For every x there is some y which makes this as false. Okay, and here there exists x, there exists y, there exists y, there exists x. When this will be true, if you find some pair for which this is true. Okay, and if you find pxy is false for all the pair x comma y, in that sense it will be false. Clear? Then we did translation. Sum of two positive integer is always positive. So here you need to define the domain first. On the basis of domain only, the logical expression will vary. Okay, that is, if you define the domain as positive integer, that is z plus, then your logical expression will be, you want x and y to two positive integer, right? So x plus y, you need sum will be positive, and this is happening for all x, for all y, x plus y, and this x and y are positive integer. And if you take the domain as only integer, then you need to give the condition that both are positive integer. That means for all x, for all y, x is positive and y is positive, then sum is positive. Okay. Then we did retranslation from logic to English, English to logic. Okay. One best friend. Here, whenever you find exactly one, you can use this there exists unique. There exists exactly one. Okay. So everyone has exactly one best friend. So bxy, you can take x has best friend y. Okay. Or y is the best friend of x. Okay. So everyone, you are talking about this everyone x, right? So for all x, there exists exactly one. There is exactly one best friend. So there exists unique y. If you take there exists y, then it will be there exists at least one. Okay. So unique y such that bxy. Okay. So this is one logical expression translation. Another is if you take for all x, there exists y. That means you need to confirm also that this is not at least one. This is exactly one, right? Okay. This y is exactly one. So bxy, and for all z which are not equal to y, for which x and z are not friends. Okay. So I think this translation is easy for this one. And if you want to go for this one, then go. This one. This is there in the book. It should be. I don't know whether it is or not. Actually, for exactly one or uniqueness, you apply this uniqueness operator. There exists unique. Okay. There exists and then exclamation sign. Then we did this translation parts. Logic to English, English to logic. Any doubt in rule of inference?
No, ma'am.
Okay, revise it. Modus ponens is if you have P implies Q and the first statement given, this one with P implies Q, okay? This one. Then Q is the conclusion. Modus tollens, if you have P implies Q and the negation of this conclusion part. Second one, right? Then negation of first one. This can be P implies negation Q and Q, right? Or you can have anything, this implies anything. These should be negation of each other. So then negation of first thing you will be having the as conclusion. Okay. Then you have H's, hypothetical self-gist. This is P implies Q, Q implies R. So this second one is same as the first one of the second. Okay. So these should match. Then you have P implies R. Then D is disjunction of P and Q, right? P disjunction Q and negation of either of this, either this one or this one. So if you have negation P, then you have only Q as the conclusion. And if you have P disjunction Q and negation of Q, the second thing, then conclusion will be P. Okay. So this is disjunctive syllogism. Then addition. If you have any statement, you can add any other statement which is not even given by using disjunction operator. Okay, that is OR operator. And simplification, from P conjunction Q, you can simplify P if you need. You can also simplify Q if you need. Okay, so from P and Q, you can simplify P as well as Q. Okay, from here, if you need somewhere Q, you can simplify that. Then you have this one, conjunction. You have two statements. P is given, Q is given. Means you are given both statements. So you can easily take the conjunction of both. That means we have P and Q. Right? Then resolution. So don't get confused between resolution and DS. In DS, we have one disjunction. Okay? And negation of the other either of these, P or Q. But here we have two disjunctions. P disjunction with Q and negation of P disjunction with R. So in that sense, this will not be the part of that. Q disjunction with R will be the conclusion because P and negation P can't exist together. Then you have P disjunction Q, negation Q, disjunction with R. In that sense, Q and negation Q can't exist together. That's why P disjunction with R will be the conclusion. Okay. Then we did this. That is, which rule of inference is the basis of these arguments. And we use this rule of inference more than one or two to get the conclusion from the given premises, from the given hypothesis. Thing is that a rule should be correct. You are applying which rule where doesn't matter. Okay. Then we did for quantified statements. So for quantified statement for all xpx and there exist xpx. So from general quantified statement for all xpx, you can find at P at some instant. That is, if C belongs to domain, obviously P will be true at that C. Okay, so this is universal from universal instant. At some instant, you are calculating it. And if it is given as PC for any arbitrary C, arbitrary means you take any element from the domain, it will be true for that. That means you can generalize it, universal generalization. That means for all xpx is true. Okay. Then you have existential instantiation. That is, from existential quantification, you are calculating at some instant that if there exists xpx, means to say you are sure that at some x it is true, right? So that some x is C. So you can calculate for PC, right? PC is true. Then if PC is given, then you can generalize it, there exists xpx. We are sure that PC is true, right? So there exists xpx is true. That is generalization, from instant to generalization. Then we did some questions based on this. Exercise questions. Any doubt in this? Yes? No. Good. Yeah. Tell me how you identify that this is the this quantified statement and there will be some predicates or quantifiers, or this is not the quantified statement. All is used, some is used, right? At least few is used. And what about this one? This is quantified or not? This statement. Not quantified,
No.
right? So this one, you are using this PQR, not X. Yeah, this one will be quantified.
Okay.
Then introduction to proof we did. So tell me any doubt if you have. So we did 3 ways, 3 proofs. One is direct proof, another is proof by contraposition, another is proof by contradiction. In direct proof, in all the statements we are just trying to prove P implies Q. Okay. So in direct proof, we take P as true. Okay, and then we prove Q. Okay. So we assume P, and by using some rules, we prove Q. Okay. In contraposition, we assume negation Q and we prove negation P. Okay. Contraposition of P implies Q, you assume negation of Q statement and you prove negation of P. In contradiction, what we try to prove, see, P is given, that we assume, and also we assume negation Q. Okay, we want to prove Q, but in place of Q, we have just assumed that what if we assume the negation Q? So obviously, if we have assumed negation Q, we will be having some wrong inference, right? Wrong derivation. That will be, we will be ended up with negation P. That will be contradiction to the given statement P, right? So that's why our assumption will be wrong. That is, Q, negation Q is wrong. So Q will be true. Okay, and that's what we wanted to prove. So P and negation Q, that is true. Okay. Negation P is false, you can't take it. No, that will not help you. Because P is already given, right? You want to prove as Q, then why you will assume the Q, right? You are going to prove is Q. Then you can't assume na Q is true. Okay. So in contradiction, actually contraposition is the part of contradiction only. If you don't assume P here, right? Okay. In contraposition, you just assume negation Q and you prove negation P. But in contradiction, you assume negation Q as well as P, right? Then you try to prove negation P. Okay. Yeah. If you want to contradict some statement, or if you want some statement
Ma'am, not audible.
proof. Yes? Oh. If you want to prove or disprove something, if for disproving something, counter example will help, right? If you want to disprove some statements, then just give the counter example. That is enough to disprove the thing. But if you want to prove thing, then Only just giving the example in the evidence of that will not be enough, right? For proving, you need to give the proof. That can be direct proof, can be contraposition or contradiction. Okay.
Yes, ma'am.
Any other doubt in chapter 1? Yes? Any other doubt in chapter
No,
1?
ma'am.
So tomorrow be prepared with chapter 2 and that algorithm part. Okay?
Okay, ma'am.
So I stop here. Thanks all.
Thank you, ma'am.